I remember the exact moment entropy stopped being an abstract concept and became real to me. I was in my kitchen making coffee. I watched the steam rise from the hot pot, little wisps of water vapor drifting into the air, spreading out, dissipating into the room. And I thought, that's entropy. That's irreversibility. That's the arrow of time. The water molecules started clustered together in boiling liquid. Now they're scattered throughout the kitchen, randomly bouncing around. The energy that made them move is still there, dissipated as heat. The molecules will never spontaneously gather back into the pot and reboil. That direction, from organized to disorganized, from concentrated to dispersed, is built into the fabric of reality. Most people think entropy means disorder, and in a loose sense, that's right. But the real meaning is deeper and stranger. Entropy is about probability. It's about how many ways something can be arranged. It's about time having a direction. It's about why you can't unbreak an egg, why hot coffee cools down but cold coffee never spontaneously heats up, why the universe is slowly dying. Entropy is why everything eventually falls apart. And that's what I want to explore in this video. Not just the technical definition, though we'll get there, but what entropy really means, why it matters, why understanding entropy changes how you see the universe. Let me start with the basics. Entropy is a measure of disorder, or more precisely, the number of ways a system can be arranged at a microscopic level while looking the same at a macroscopic level. But that definition doesn't capture why entropy is so important. Let me try a different angle. Imagine you have a gas in a box. The gas molecules are bouncing around randomly, colliding with each other in the walls. There are an astronomical number of possible arrangements of these molecules. Each specific arrangement has the same total energy. The molecules are moving at the same speed, on average, but they could be arranged in infinitely many ways. Now imagine you put a divider in the box, trapping half the gas on one side. The gas on one side is organized in a sense. It's confined to a smaller space. If you remove the divider, the gas will spread out to fill the entire box. The gas molecules have more possible arrangements when they're spread out. That's entropy increasing. The gas has become more disordered in the sense that there are more possible microstates consistent with the same macroscopic state. Here's the key insight. Entropy increases not because the universe is trying to be disorderly, but because there are simply more ways for a system to be disorderly than ordered. If you have 1,000,000 molecules to arrange, there are vastly more arrangements where they're spread throughout the whole box than arrangements where they're confined to one corner. Simple probability means the system will naturally evolve toward the more common state, maximum entropy. This is the second law of thermodynamics. In an isolated system, entropy always increases or stays the same, never decreases. This law is one of the most fundamental principles in all of physics. The first law says energy is conserved. It doesn't appear or disappear, just changes form. The second law says energy tends to disperse and spread out. If you have organized energy, concentrated heat, it will naturally spread out and become disorganized. The process is irreversible. This is why hot coffee cools down. The coffee is hot because its molecules are moving fast, concentrated in one place. The air around it is cold because its molecules are moving slowly and are spread out. Heat spontaneously flows from the hot coffee to the cold air. The energy disperses. Entropy increases. The reverse process, cold air spontaneously heating the coffee while becoming colder, is theoretically possible but vanishingly unlikely. So unlikely that if it happened, you'd see that billions of times in a row before it would occur even once by pure chance. The second law doesn't forbid the reverse process. It just says it's overwhelmingly improbable. But here's where it gets profound. The second law is the only fundamental law of physics that has a direction in time. Newton's laws work the same backward and forward. Quantum mechanics works the same backward and forward. But the second law has an arrow. Entropy increases. Time flows forward. You can't turn back. This is why you can. Remember the past, but not the future. It's why you can influence the future, but not the past. It's why videos of eggs unbreaking look absurd and impossible, because they are. Entropy makes time flow in one direction only. Let me explore this more deeply. Physicists used to be troubled by this asymmetry. If the fundamental laws of physics work the same backward and forward, why does time have a direction? Why do we experience time as flowing from past to future rather than the reverse? The answer is entropy. At the Big Bang, the universe started in a state of extraordinarily low entropy, extremely organized, all the matter and energy concentrated and hot. Since then, entropy has been increasing. The universe has been spreading out, cooling down, becoming more disordered. The direction of increasing entropy defines the forward direction of time. This is called the arrow of time, or the thermodynamic arrow. It's not just a feature of our universe, it's a feature of reality itself. Now here's something fascinating. The second law is statistical. It's not absolute. In principle, you could have a scenario where entropy decreases. All the air molecules in a room could randomly bounce around and end up in one corner, leaving a vacuum in the rest of the room. This wouldn't violate any fundamental laws. It's just so monumentally unlikely that it would take longer than the age of the universe to observe once by pure chance. How unlikely? Imagine 1 septillion 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 times more unlikely than that. That's genuinely not an exaggeration. The numbers involved are so large they're beyond comprehension. So while entropy decrease is possible in principle, it's so improbable that we can treat the second law as absolute for all practical purposes. This raises a philosophical question. If entropy decrease is physically possible, just incredibly unlikely, what makes something possible versus just astronomically improbable? Is there a real distinction, or is possibility just a matter of degree? This touches on deep issues about the nature of physical law. Are the laws of physics truly absolute, or are they statistical rules that usually hold? Does randomness and probability operate at the level of individual particles, with higher level laws arising as statistical generalizations? The answer is yes to the latter interpretation. At the quantum level, individual particles behave probabilistically. At the macroscopic level, statistics guarantee that the second law holds. We observe the world through macroscopic measurements, so we never see entropy decrease. Let me talk about what entropy actually is more formally. In thermodynamics, entropy is defined as the heat added to a system divided by the temperature at which that heat is added. Mathematically, S equals Q over T, where S is entropy, Q is heat, and T is temperature. This definition comes from looking at how systems behave when they exchange heat. If you add heat to a system, its entropy increases. If you remove heat, its entropy decreases. But the key is that the amount of entropy change depends on the temperature. Adding heat to a hot system increases its entropy less than adding the same amount of heat to a cold system. This is because hot systems already have high entropy. Their molecules are already moving around randomly. Cold systems have lower entropy, so adding heat increases it more. But there's a deeper definition from statistical mechanics. Entropy is related to the number of possible microscopic states consistent with a given macroscopic state. Imagine you have a deck of cards. If the cards are shuffled randomly, there are about 52 factorial possible arrangements. That's 52 times, 51 times, 50 times, times 1, which is around 10 to the power of 68 different orderings. Each arrangement is equally likely if you shuffle randomly. Now imagine you organize the cards by suit and rank. There's only one such ordering, or a few if you allow different orderings within suits. This ordered state has far fewer possible microstates. If you shuffle the cards repeatedly, they'll almost certainly end up in random disorder, simply because there are so many more disordered arrangements than ordered ones. Not because the universe prefers disorder, but because mathematically, disorder is far more common. The same principle applies to molecules in a gas. Organized states, like all molecules on one side of a box, have fewer possible microstates. Disorganized states, molecules spread throughout, have exponentially more. Pure probability means organized states rarely occur. Ludwig Boltzmann defined entropy as S equals KLN of W, where K is Boltzmann's constant and W is the number of possible microstates. This equation relates the thermodynamic entropy to the statistical properties of the system. This definition makes it clear entropy isn't about the universe's preference for disorder, it's about probability. The second law isn't a law of nature trying to enforce disorder, it's a law of probability. Most states are disordered, so systems naturally evolve toward them. Now let me talk about entropy in everyday life. You experience entropy constantly. You see it every time something breaks and can't spontaneously fix itself. Every time heat flows from hot to cold. Every time you burn fuel and the energy disperses as waste heat. Every time you age and your biological systems gradually deteriorate. Aging is actually a great example of entropy. When you're born, the cells in your body are organized, reproducing accurately, maintained by biological systems. Over time, entropy increases. DNA accumulates mutations. Proteins misfold. Cells accumulate damage. Systems degrade. You age and eventually die. This isn't because of some cosmic force against you, it's statistics. Disorganized biological systems are far more common than organized ones. Your body can repair itself for a while, but eventually the random damage accumulates faster than it can be repaired. Entropy wins. Heat death of a burning candle is another example. The candle has chemical energy locked in the wax. When you burn it, that energy is released as heat and light. The heat disperses into the environment. The light radiates away. The organized energy in the candle becomes disorganized waste heat. The process is irreversible. You can't collect all that dispersed heat and rebuild the candle. This is why perpetual motion machines are impossible. Any machine you build will dissipate some energy as heat through friction. You can never get more energy out of a system than you put in, because some always escapes as waste heat. The second law makes perpetual motion impossible, not because the laws forbid it, but because it's statistically impossible. This also explains why the universe is gradually cooling. Energy constantly spreads out. The sun fuses hydrogen and releases energy. That energy radiates into space. Stars burn out. Black holes evaporate. Eventually, all usable energy will be dispersed as low-temperature radiation spread uniformly throughout space. This is the heat death of the universe. Maximum entropy. All energy dispersed, nothing organized, nothing changing. It will take an incomprehensibly long time, 10 to the 100th power years or more. But thermodynamically, it's inevitable. The second law guarantees it. Let me talk about information entropy. Entropy isn't just a thermodynamic concept, it appears in information theory too. In fact, the concept is the same, just applied to information rather than energy. Information entropy measures the amount of uncertainty or randomness in a set of data. If you have a string of bits that's completely random, equal probability of 0 or 1, that string has maximum entropy. If the string is predictable, like all zeros, it has minimum entropy. This is why compression works. A random string of data can't be compressed much because there's no pattern to exploit. But a string with lots of redundancy, lots of structure can be compressed because you can describe it more efficiently by noting the patterns. This connection between information entropy and thermodynamic entropy is profound. Claude Shannon, who developed information theory, noticed the mathematics was identical to Boltzmann's entropy equation. This isn't a coincidence. Information and physical entropy are related at a deep level. When you erase information, you increase entropy. When you compute, you dissipate energy as heat. Every computation releases waste heat proportional to the amount of information erased. This is called the Landauer limit. You can't compute without dissipating energy. The second law doesn't allow otherwise. This has implications for artificial intelligence and computing. As computers get faster and more powerful, they're limited by thermodynamics. Every operation dissipates heat. Eventually, if you want to increase computational power while staying within a finite space and energy budget, you hit the entropy limit. Physics sets a hard ceiling on computation. Now let me talk about one of the strangest aspects of entropy, Maxwell's demon. In 1867, James Clerk Maxwell proposed a thought experiment. Imagine a demon at a tiny door between two gas chambers. The demon can see individual molecules. When a fast-moving molecule approaches from the left, the demon opens the door to let it through to the right chamber. When a slow molecule approaches from the right, the demon lets it through to the left chamber. Over time, the right chamber fills with fast molecules, hot gas, and the left with slow molecules, cold gas. Heat has flowed from cold to hot without doing work. This seems to violate the second law, but it doesn't. The demon needs to observe the molecules, and observation requires exchanging photons or other particles with the molecules. This observation and the demon's deliberation about whether to open the door dissipates heat. When you account for the entropy cost of the demon's information processing, the total entropy increases. The second law holds. This shows that information and entropy are deeply connected. To decrease entropy by sorting molecules, you need information. Processing that information costs energy. The entropy cost of processing exceeds the entropy decrease you achieve. This is why you can't reduce entropy without expending energy. The universe won't let you cheat the second law. Actually, let me talk about black holes and entropy, because this is where entropy gets truly weird. Black holes have entropy. This was discovered by Jacob Bekenstein and Stephen Hawking in the 1970s. The entropy of a black hole is proportional to the area of its event horizon, the point of no return. This is strange because it reverses our intuition. You'd think the entropy inside a black hole would be enormous. After all, matter and energy are compressed to extreme densities, but the entropy is actually proportional to the surface area, not the volume. This violates our normal expectations about entropy. The connection to information is key. When something falls into a black hole, information about it is lost. From outside, you can never know what went in. The black hole horizon scrambles the information. This information loss increases entropy. Hawking discovered that black holes aren't entirely black. They emit radiation, Hawking radiation, due to quantum effects near the event horizon. This radiation carries away energy. Slowly, a black hole evaporates. Here's the profound part. As a black hole evaporates, its entropy decreases. Its event horizon gets smaller, so the area decreases, so entropy decreases. This seems to violate the second law, but it doesn't violate it for the black hole plus the surrounding universe. The radiation emitted carries entropy into the environment. The total entropy still increases. The second law holds. The connection between black hole entropy and information is still being explored. It touches on deep questions. What happens to information that falls into a black hole? Does it destroy information, or is it scrambled in the radiation? Can information be recovered? These questions are leading to new insights about the relationship between quantum mechanics, gravity, thermodynamics, and information theory. Now let me talk about reversibility and irreversibility. One of the most profound aspects of entropy is that it distinguishes between reversible and irreversible processes. A reversible process is one that can be undone without increasing entropy. In practice, no real process is truly reversible. There's always some dissipation, some friction, some heat lost. But you can get arbitrarily close to reversibility if you slow a process down and minimize energy loss. An irreversible process is one that always increases entropy. Burning fuel, mixing two gases, heating an object through friction, these are irreversible. They can never spontaneously reverse. The distinction is crucial. It determines what's possible. Reversible processes conserve energy with perfect efficiency. Irreversible processes always lose energy as heat. They can never be perfectly efficient. This is why all real engines have efficiency less than theoretical maximum. The Carnot efficiency sets an upper limit based on the temperatures of the hot and cold reservoirs. No real engine reaches this limit because all real processes are irreversible and dissipate energy. Now here's a troubling question. The fundamental laws of physics are reversible. If you knew the exact state of every particle in a system and could reverse all their velocities, the system would evolve backward in time, exactly retracing its path. But thermodynamic laws are irreversible. Entropy increases forward in time, never backward. How can irreversible laws arise from reversible underlying laws? The answer involves coarse graining and information. At the microscopic level, physics is reversible, but we never observe the microscopic level. We observe coarse-grained macroscopic properties. When you coarse grain, when you ignore information about which exact microstate you're in, and only observe the macroscopic state, reversibility is lost. Irreversibility emerges from reversible laws through information loss. This is profound. Irreversibility isn't fundamental. It's an artifact of incomplete information. If you had perfect microscopic information, you could reverse any process. But perfect information is unattainable. So irreversibility is effectively fundamental for any observer with finite information. Time's arrow, the fact that time flows in one direction, is rooted in this. The forward direction of time is the direction of increasing entropy. The backward direction would be decreasing entropy. Both are physically possible at the microscopic level. But at the macroscopic level where we live, entropy increase is overwhelmingly likely. So time flows forward. That's simply the statistical direction. Let me talk about entropy in the universe as a whole. The universe started at the Big Bang in a state of extremely low entropy. It was incredibly organized. All matter and energy concentrated in an infinitely dense point. Since then, entropy has been increasing. The universe has expanded. Matter has clumped into structures that eventually burn out. Stars have fused hydrogen into heavier elements and radiated energy into space. Entropy has increased. But here's something interesting. The universe has become more complex. Life emerged. Galaxies formed. Stars, planets, biology. How can the universe become more complex if entropy is increasing? The answer is that complexity is possible even with increasing entropy. Localized complexity can increase if entropy increases faster somewhere else. When you digest food, you break down ordered molecules and convert them into heat, entropy increasing overall. But the energy you extract allows you to build complex structures, proteins, cells, neurons. Your local entropy might decrease, you become more organized, but your total entropy, including the heat you dissipate, increases. The same is true for the universe. Stars form from gas clouds, becoming more concentrated, lower entropy locally, but they burn hydrogen, radiate heat, increase entropy. The total entropy increase is larger than the local decrease. The universe can create complexity because it's far from equilibrium. As long as energy can flow through the system, creating gradients between hot and cold, energy and matter can organize into complex structures. But eventually those gradients will dissipate. The sun will burn out. All stars will die. The universe will reach maximum entropy, heat death. At that point, no more complex structures can form. Everything will be at the same temperature, evenly distributed, utterly random. Actually, let me correct that slightly. Even at maximum entropy, quantum fluctuations will still occur. Regions will spontaneously organize briefly, then dissipate. But such fluctuations will be vanishingly rare and brief. For all practical purposes, the universe will be dead, no stars, no structure, no change. Let me talk about the relationship between entropy and time from a philosophical perspective. Why do we remember the past but not the future? Why is there a difference between past and future? At the quantum level, there's no difference. Quantum mechanics is time symmetric. Entropy is the explanation. Your memories are ordered structures in your brain. Creating a memory increases entropy. You dissipate heat. Forgetting erases that ordered structure and increases entropy further. Your brain naturally forgets because entropy increases faster through forgetting than remembering. You can remember the past because memories were created in the past when entropy was lower. You can't remember the future because those memories haven't been created yet. Creating them would require traveling backward in time, living through the future again, which is impossible because time only flows forward. The arrow of time is built into thermodynamics. It emerges from the statistical tendency toward higher entropy. It's not a fundamental asymmetry in the laws of physics. It's a consequence of starting conditions. The universe began in low entropy. That creates an arrow. If the universe somehow started in high entropy, time's arrow would point backward. This is actually a profound insight. The laws of physics don't impose a time direction. Initial conditions do. The Big Bang set initial conditions with low entropy. which created an arrow of time. If the universe somehow reversed and recontracted toward a big crunch, time's arrow might reverse too, at least according to some interpretations. Now, let me talk about practical applications and implications of entropy. Understanding entropy is crucial for engineering. Every technology relies on thermodynamic principles. The efficiency limits of engines, refrigerators, air conditioners are all set by entropy. You can't build a perpetual motion machine because entropy forbids it. You can't extract perfect work from heat without some waste. Entropy also limits information technology. Erasing information costs energy. Computing dissipates heat. As computers get more powerful, they're constrained by thermodynamics. Eventually, if you want exponential growth in computation, you hit entropy limits. Climate change is partly an entropy problem. Burning fossil fuels takes ordered chemical energy and converts it to disordered heat, increasing entropy. The waste heat goes into the atmosphere. This disrupts the climate. A complex, ordered system becomes more chaotic. Entropy increases. Aging is entropy. Your body needs to constantly fight entropy to stay alive. Repairing damage, removing waste, maintaining organization. When you die, entropy takes over. Your body decays. Organized structures break down into disorder. Entropy increases. Death itself is the ultimate entropy victory. A living organism is a highly ordered structure, maintained far from equilibrium. Death is the relaxation toward equilibrium. Disorder, decay, entropy increase. Understanding this doesn't make it less tragic, but it reframes it. Death isn't evil or cruel. It's thermodynamic necessity. Life is the remarkable thing, the temporary local decrease in entropy, maintained by metabolizing energy. It's beautiful precisely because it's temporary and improbable. Entropy is one of the most profound concepts in physics. It explains why time flows in one direction. It sets limits on what's possible. It determines the fate of the universe. It explains irreversibility, aging, death, information, consciousness. Most people never think about entropy. They go through life without realizing this fundamental principle underlies everything they experience. But once you understand entropy, you see it everywhere. In every cup of coffee cooling down, in every physical system degrading, in every moment you remember the past but can't see the future, in the aging of stars and the eventual heat death of the universe. Entropy is why the universe is the way it is. It's why time flows forward. It's why you can't unbreak an egg. It's why everything eventually falls apart. And that's okay. That's beautiful. That's the fundamental nature of reality. Understanding entropy doesn't make the universe less mysterious. It makes it more so. It raises deeper questions. Why did the universe start in low entropy? Is that a coincidence or necessity? Could the universe end and begin again in cycles? What role does entropy play in consciousness and observation? These questions remain open, but they all flow from this one profound principle. Entropy always increases. Thanks for watching. I want to go deeper into the mathematics because that's where entropy truly reveals itself. Boltzmann's equation, S equals KLN of W, is deceptively simple, but it contains profound truths. W is the number of possible microscopic arrangements, microstates, consistent with a given observable macroscopic state. K is Boltzmann's constant, which converts between molecular scale physics and human scale thermodynamics. The logarithm is crucial because it makes entropy additive. Let me unpack this with an example. Suppose you have a container with 10 distinguishable gas molecules. If you want all 10 on the left half of the container, there's exactly one way. To achieve that, all 10 molecules must be on the left, so W equals 1. If you want them evenly distributed, 5 on the left and 5 on the right, how many ways can you arrange that? You need to choose 5 molecules out of 10 for the left side. That's C10(5) equals 252 different ways. So W equals 252. If you want them maximally dispersed with random distribution, the number of possible arrangements becomes astronomical. For realistic numbers, say 10 to the 23rd power molecules, the number of maximally dispersed arrangements is incomprehensibly larger than ordered arrangements. The logarithm of W gives you the entropy. The larger W is, the higher the entropy. This makes intuitive sense. More possible arrangements means more disorder, or more ways to be disordered. But here's what's profound. If you have two independent systems with W1 and W2 arrangements respectively, the combined system has W1 times W2 possible arrangements. Taking the logarithm of the product gives you the sum of the logarithms. Natural log of W1 times W2 equals natural log of W1 plus natural log of W2. So entropies add when systems combine. This is crucial. It means entropy is an extensive property. It scales with system size. Doubling the amount of gas in a box increases entropy by a fixed amount. This is consistent with experiment, and it validates Boltzmann's definition. Now let me address a common misconception. Entropy isn't the same as disorder, even though people often use those terms interchangeably. Disorder, in everyday language, means things are scattered or disorganized. But entropy is specifically about the number of possible microscopic arrangements. A room with books thrown everywhere might look disordered, but if we're tracking individual molecules in the air, the number of possible arrangements is the same whether the books are organized or scattered. The book's configuration doesn't affect gas molecule entropy significantly. When physicists say entropy is disorder, they mean a technical definition. Microstates corresponding to configurations indistinguishable at the macroscopic level. A gas spread throughout a container has more indistinguishable microstates than a gas confined to one corner. That's why we call it more disordered. But the core is probability, not disorder. It's that there are more ways to be spread out than concentrated. This distinction matters because it clarifies what the second law actually says. It's not that the universe prefers disorder. It's that statistically disorganized states are more probable because there are more of them. Let me talk about the Gibbs entropy formula, which extends Boltzmann's definition. For a system with multiple possible macrostates, xi, each occurring with probability pi, the Gibbs entropy is S equals minus k, sum over ipi, natural log of pi. This is a more general formula that works for systems not in thermal equilibrium. It says entropy is higher when there's more uncertainty about which state you're in. This formula appears in information theory too. In information theory, if you have a message where different symbols appear with different probabilities, the Shannon entropy is S equals minus the sum over I of pi log base 2 of pi. The formula is identical up to changing the logarithm base. This shows that thermodynamic entropy and information entropy are deeply connected mathematically. When you don't know something, when you have uncertainty, entropy is high. When you know the exact state, certainty, entropy is low. This is why Maxwell's demon fails. To decrease thermodynamic entropy, the demon needs information. But gathering information increases the entropy of the demon's recording system. Entropy always increases when you account for all information-related processes. Life is a process of fighting entropy locally while allowing it to increase globally. A living organism is an ordered structure. Your cells, tissues, organs, they're arranged in specific ways, maintained with incredible precision. This organization is antithetical to entropy. An entropy maximizing system would be chaotic. Molecules jumbled randomly, proteins misfolded, structures dissolved into disorder. But life maintains this order through constant work. You eat food, extract energy from it, use that energy to maintain your biological organization. In doing so, you produce waste, heat, disorder, entropy. The total entropy of you plus your environment increases, satisfying the second law. This is why living systems require constant energy input. A plant needs sunlight. Set, animal needs food. Without continuous energy flow, organisms can't maintain their ordered structure. Entropy takes over. Death is when entropy finally wins. When you die, your body stops consuming energy. Your biological systems stop working. Entropy increases rapidly. Your ordered biological structures decay into disorder. Bacteria colonize your body, breaking down proteins, lipids, nucleic acids. Your organized body becomes chaos. This is why death is irreversible. You can't restore a dead body to life just through chemistry, because that would require decreasing entropy locally without compensating increase elsewhere. You'd need an external energy source and precise control, rebuilding the dead body's entire organization. Even theoretically, this is essentially impossible. Aging is a manifestation of entropy at the cellular level. DNA accumulates mutations, random errors that decrease the fidelity of genetic information. Proteins misfold, aggregate into useless structures. Mitochondria, the energy-producing organelles, accumulate damage and function less efficiently. Your cell's error correction mechanisms work hard to maintain organization, but eventually random damage exceeds repair capacity. This is why aging is thermodynamically inevitable. Maintaining perfect biological order requires infinite energy and infinite vigilance. No organism can achieve that. Random damage accumulates. Entropy increases. Aging happens. Death follows. Cancer is partly an entropy problem. Your cells normally have tight controls on reproduction and mutation. Cancer occurs when these controls break down, when random mutations accumulate in genes controlling cell division. The cancer cell population becomes more variable, more diverse, higher entropy. It's entropy taking over the cellular level. This is a dark way of thinking about biology, but it's accurate. Life is temporary rebellion against entropy. It's a local decrease in entropy maintained by metabolizing energy. Eventually, the rebellion fails. Entropy always wins. But that doesn't make life meaningless. If anything, it makes it more meaningful. Life is remarkable precisely because it's improbable. Consciousness is extraordinary because it shouldn't exist according to thermodynamic principles. Yet here we are, conscious, aware, capable of understanding entropy itself. Understanding that we're fighting entropy might seem depressing, but it's liberating too. It explains biological drives, why you hunger, energy needed, why you sleep, cellular repair, why you seek connection and reproduction, genetic continuation. These aren't moral imperatives. They're expressions of the physical law that life must continually work against entropy to persist. Why does time flow forward and not backward? This is one of physics' deepest questions, and entropy provides the answer. The fundamental laws of physics, Newton's laws, quantum mechanics, general relativity, are time symmetric. They work identically forward and backward in time. If you took a video of particles interacting and played it backward, The interactions would obey the same laws. Yet we experience time as having a direction. We remember the past, not the future. We can influence the future, not the past. Videos of things reversing, eggs unbreaking, coffee heating itself while the environment cools, objects jumping upward for no reason, look impossible because they violate thermodynamics. Thermodynamics breaks time symmetry. The second law says entropy increases in the forward direction of time. It decreases in the backward direction. This creates an asymmetry. Time flowing forward is the direction of increasing entropy. Backward is decreasing entropy. But here's the puzzle. If fundamental laws are time symmetric, why does entropy increase in one direction? Where does the asymmetry come from? The answer is initial conditions. The universe started in the Big Bang with extraordinarily low entropy. All matter and energy was concentrated in an infinitely dense, infinitely hot point. This wasn't a random state. It was a highly special, extremely unlikely state. As the universe evolved, entropy increased. The cosmos expanded, cooled, structures formed, stars burned out, always in the direction of increasing entropy. Time's arrow is defined by this direction. The forward direction of time is the direction the universe has been evolving since the Big Bang. Backward is the impossible direction where entropy decreases. This is profound. Time doesn't have an intrinsic direction. The laws of physics don't favor forward over backward, but the universe's history does. Because the universe started in low entropy and has been increasing ever since, that defines forward. If the universe reached maximum entropy, heat death, would time stop? In a sense, yes. At maximum entropy, nothing changes. No entropy can increase further. So the arrow of time would no longer point anywhere. Everything would be static, unchanging, eternal. Some physicists have speculated about universe cycles. Maybe the universe expands, reaches maximum entropy, then contracts back toward a big crunch. During expansion, entropy increases and time flows forward. During contraction, entropy might decrease and time might flow backward. We'd experience this as living in a universe where entropy increases. We always experience time as flowing toward higher entropy, regardless of whether the universe is expanding or contracting. This is speculative, but it illustrates how deeply entropy is tied to the arrow of time. Psychologically, the arrow of time is experienced through memory. You remember the past because your memories are ordered structures in your brain. Creating a memory requires energy expenditure, increasing entropy. Organizing neural patterns, locally decreasing entropy. But the total entropy increase exceeds the local decrease. You don't remember the future because those memories haven't been created yet. To remember the future, you'd need to experience it first, create the memory, then travel backward in time to before you experienced it. That's impossible. Your sense of free will is also tied to the arrow of time. You feel like you can choose to do something. You have genuine options for the future, but the past seems fixed. You can't change what happened. Thermodynamically, this makes sense. Your present state was determined by the past, with quantum randomness. Your choices slightly affect the future. The future is still being determined. The past is fixed. Forward in time from low entropy to high entropy is the direction where the future is undetermined and you have agency. Backward in time from high entropy to low entropy would be a direction where the future is fully determined by the past and you have no genuine choices. Time's arrow isn't just a physical phenomenon. It's deeply connected to how consciousness works, how memory functions, how choice and agency operate. The connection between entropy and information is one of the most profound insights in 20th century science. In 1948, Claude Shannon developed information theory, which provides a mathematical framework for understanding information, communication, and compression. He defined a quantity called Shannon entropy, which measures the average uncertainty in a message. If a message consists of symbols with different probabilities, Shannon entropy is higher when the probabilities are uniform, maximum uncertainty, and lower when some symbols are far more common, less uncertainty. Remarkably, Shannon entropy has the exact same mathematical form as Boltzmann entropy. S equals minus the sum of P sub I log of P sub I. This isn't a coincidence. The same principle applies. Uncertainty is high when there are many possible configurations. Certainty is high when configurations are rare. This connection reveals something profound. Information and entropy are linked at a fundamental level. When you store information, you're creating an organized structure, a low entropy configuration. When you erase information, you increase entropy. The Landauer limit quantifies this. Erasing one bit of information requires at least kb times. T times natural log of 2 joules of energy dissipated as heat, where T is temperature and kb is Boltzmann's constant. This has astonishing implications for computing. Every computation involves erasing information. Every logical operation erases the bits that were inputs to previous operations. Therefore, every computation must dissipate heat. Computing cannot be perfectly efficient from a thermodynamic perspective. As computers become more powerful, they must dissipate more heat. The energy cost of computation isn't just an engineering problem, it's a fundamental physical constraint set by thermodynamics. Some researchers have explored reversible computing, performing computations that don't erase information, so theoretically no heat must be dissipated. In principle, reversible computing could achieve zero heat dissipation. But in practice, it's extraordinarily difficult because you must prevent any information from being lost. The Landauer limit sets a minimum energy cost for any computation that erases information. This is a profound constraint on the future of artificial intelligence. As AI becomes more complex, more powerful, it must dissipate more energy. There's a thermodynamic cost to intelligence. In black hole thermodynamics, this connection between information and entropy becomes even stranger. When something falls into a black hole, information about it is lost from the external universe. From outside, you can never know what went in. Stephen Hawking showed that this information loss is related to the entropy of the black hole. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is counterintuitive. Normally, entropy increases with volume. But black hole entropy is different. It's related to the amount of information that can be stored on the event horizon. This led to the holographic principle. All the information in a volume of space can be encoded on its boundary surface. A black hole is the ultimate holographic system. All its information is encoded on the event horizon. This remains one of the deepest mysteries in physics. How is information encoded on a black hole's event horizon? Where does information go when it falls in? Is it destroyed or encoded in subtle correlations in Hawking radiation? Some researchers believe information is preserved, that a black hole eventually completely evaporates, returning all information to the outside universe in the radiation. Others believe information is lost forever. The answer will probably require a full theory of quantum gravity to understand. But the connection is clear. Information, entropy, and black holes are fundamentally linked. Understanding entropy is key to understanding quantum gravity and the deepest structure of reality. The universe as a whole is an entropy problem on the grandest scale. The Big Bang created the universe in an extraordinarily low entropy state. All matter and energy was concentrated in a single point, the lowest entropy possible for any macroscopic system. Since then, entropy has been increasing relentlessly. The universe expanded, matter spread out, stars formed and burned, energy dispersed, entropy increased. But here's a puzzle. If the second law says entropy always increases, why did the universe start in such low entropy? That seems to violate the spirit of the law. Shouldn't the universe start in maximum entropy? This is called the low entropy problem of cosmology. The initial low entropy of the Big Bang is one of the greatest mysteries in physics. Some possibilities. First, maybe there's a biological selection effect. Observers require low entropy. They require organization, structure, life. Only in low entropy universes can observers exist. So naturally, we find ourselves in a low entropy universe. This is an anthropic argument. Second, maybe the Big Bang itself imposed low entropy. If the Big Bang created space and time, maybe it necessarily created them in a specific organized state. We don't know enough about quantum gravity to say. Third, maybe there's a fundamental law we don't yet understand that explains why the universe started in low entropy. Fourth, maybe the universe is cyclical. Maybe it expands from a Big Bang, reaches maximum entropy, then somehow contracts back to a big crunch, which bounces to another Big Bang. Each cycle starts fresh at low entropy. We live in one cycle among infinitely many. Fifth, maybe entropy is more subtle than we think. Maybe what we call high entropy isn't actually maximal. Maybe maximum entropy is even higher, but more stable. Low entropy states are actually more likely than we thought. None of these explanations is satisfactory. We truly don't understand why the universe started in low entropy. It remains one of physics's greatest puzzles. The implications for the far future are clearer. The universe is expanding and accelerating. Entropy is increasing. Eventually, the universe will reach maximum entropy, heat death. At heat death, all energy is dispersed uniformly as radiation at the same temperature. No gradients remain. No structures exist. Nothing changes. The universe is dead, not destroyed, but static, unchanging, eternal. This will take an incomprehensibly long time, trillions of years for stars to burn out, 10 to the power of 100 years for black holes to evaporate, even longer for proton decay and other processes. But the direction is fixed. Entropy increases. Heat death is inevitable. Some cosmologists have explored what happens after heat death. In an infinite time after heat death, quantum fluctuations might create brief pockets of order. Boltzmann brains, conscious entities arising from quantum fluctuations, might appear infinitely many times, separated by infinite periods of unchanging void. Or the universe might somehow tunnel into a new phase of expansion, a new Big Bang, a new cycle. We don't know, but we know the direction. Entropy increases. That's the arrow pointing into the far future. Understanding entropy has transformed technology and our ability to manipulate the physical world. Heat engines are designed to extract useful work from heat flow. A Carnot engine is the theoretical maximum efficiency heat engine. It operates between a hot reservoir and a cold reservoir, extracting heat from the hot side, converting some to work, and dumping the rest into the cold side. The Carnot efficiency, maximum fraction of heat convertible to work, is ETA equals 1 minus T sub C over T sub H, where T sub C and T sub H are the cold and hot temperatures. Notice that perfect efficiency, ETA equals 1, will require T sub C equals 0, absolute 0, or T sub H equals infinity. Neither is achievable, so perfect efficiency is impossible. This is another consequence of the second law. Every real engine has efficiency less than Carnot efficiency because real engines are irreversible. They dissipate energy as heat through friction and other inefficiencies. Refrigerators and air conditioners work by pumping heat from cold to hot using work input. They rely on thermodynamic principles to maintain temperature gradients. Power plants, whether coal-fired, nuclear, solar thermal, or otherwise, all ultimately work by creating a temperature gradient and extracting work from it. The waste heat must go somewhere, usually into rivers, oceans, or the atmosphere. This waste heat increases the entropy of the environment. This is why power generation efficiency is limited. No power plant can convert all chemical or thermal energy into electricity. Some fraction must be wasted as heat. Entropy requires it. Information technology faces entropy limits too. Computers dissipate heat. Processors generate waste heat. Data centers, the farms of thousands of computers powering internet services, consume enormous amounts of electricity. Much of it becomes waste heat. As computers become faster and more powerful, they must dissipate more heat. The Landauer limit sets a fundamental lower bound on the heat generated per computation. Future quantum computers will face the same issue. Even theoretically perfect quantum computers must dissipate some heat to function. Refrigeration technology relies on entropy principles. A refrigerator pumps heat from a cold interior to a warm exterior, creating a temperature gradient. This requires work input. The work is ultimately dissipated as heat into the surroundings. The total entropy of the refrigerator plus environment increases, satisfying the second law. Materials science relies on understanding entropy. The properties of materials depend on their atomic and crystalline structure. Creating ordered structures, low entropy, requires energy. Heating materials causes atoms to vibrate more, creating disorder, increasing entropy. The melting point of a material is where thermal energy overcomes the ordering forces. Chemical reactions proceed based on entropy, both the entropy of the system and the entropy of the surroundings. A reaction can occur spontaneously if the total entropy, system plus environment, increases. Climate change is partly an entropy problem. Burning fossil fuels takes ordered chemical energy and converts it to disordered heat. This increases entropy globally. The waste heat goes into the atmosphere and oceans, disrupting climate patterns. Alternative energy sources like nuclear, solar, and wind also generate heat, but they do it with greater efficiency and without greenhouse gas emissions. Evolution is an entropy phenomenon, though it often doesn't seem that way. Life creates order, complex organisms with organized structures. DNA contains information. Proteins fold into specific shapes. Cells organize into tissues. Brains create thoughts. If evolution creates order, doesn't it violate the second law? No, because evolution is possible only with energy input from the sun. Plants capture solar energy through photosynthesis. Animals eat plants or other animals. The energy flows through living systems, creating order locally while increasing entropy globally. The sun generates vast amounts of energy through fusion, converting hydrogen to helium. This energy radiates outward. Earth captures a tiny fraction. Plants use that energy to build complex molecules. Animals use that energy to move and think. All the while, waste heat is generated, energy dispersed. Entropy increases globally. Evolution is selection for order in the presence of abundant energy. Natural selection favors organisms that are good at capturing and using energy. More efficient photosynthesis, better predators, more sophisticated brains. All are ways organisms compete to capture and metabolize energy. Sexual reproduction creates genetic diversity. Mutations introduce variation. Natural selection chooses which variants survive and reproduce. Over generations, organisms become more complex, more adapted to their environment. This might seem to decrease entropy, organisms becoming more ordered, but the sun is dissipating energy, entropy is increasing there. Earth receives a tiny fraction of solar energy. Life uses that to create order locally. The total entropy of the sun, Earth, and life increases. The second law is satisfied. Interestingly, the information in DNA can be understood through the lens of entropy. DNA stores information. This information is low entropy, highly organized. Creating and maintaining DNA requires energy. Replicating DNA requires energy. Fixing errors in DNA requires energy. When DNA replicates, errors, mutations, occur. Most mutations decrease fitness. They reduce the organism's ability to survive and reproduce. Natural selection removes these low fitness organisms. But occasionally, a mutation increases fitness. The organism adapts to its environment better. The mutation spreads. This process, mutation and selection, gradually accumulates advantageous mutations while removing deleterious ones. Information accumulates in DNA. Organisms become more complex. But this complexity is only possible because energy is flowing through biological systems. Cut off the energy, stop the flow of solar energy, and organisms cease to grow in complexity. They degrade. Entropy takes over. Evolution is a race between entropy and energy flow. Energy input allows life to create order. Entropy increase forces life to adapt, compete, and evolve. Life doesn't violate the second law. It exploits it. Life uses energy gradients created by the sun and primordially by gravitational collapse and nuclear processes to create and maintain ordered structures. In doing so, it produces waste heat and increases entropy. This is true for the entire history of life on Earth and will remain true until the sun dies in about 5 billion years. Then Earth's steady energy input will end. Life will decline. Entropy will take over. Order will give way to chaos. Entropy has profound philosophical implications that extend far beyond physics. First, entropy provides an objective definition of time's direction. Time isn't an illusion or a convention. It has a real, physical direction, the direction of increasing entropy. This direction emerges from physics, not from human perception. This means the future is genuinely different from the past in a physical sense. The past has lower entropy. The future will have higher entropy. This asymmetry is real and fundamental. Second, entropy explains why we can't reverse the past, but can influence the future. The past is a low entropy state. Creating that state required specific initial conditions in evolution. Reversing to create the same low entropy state is so improbable it's essentially impossible. The future is high entropy. Many possible states are consistent with the future's high entropy. Our actions now influence which high entropy future state is realized. We have genuine agency in affecting the future. Third, entropy poses a challenge to free will and determinism. If the universe is deterministic, if all future states are determined by initial conditions and the laws of physics, then do we have free will? The answer might be nuanced. Even if the universe is deterministic, from our perspective with limited information, the future is uncertain. We can't predict the future perfectly. Because we don't have perfect information about current conditions, in that sense, our choices are free in that they're not predetermined by anything we can know. We genuinely can't predict our own choices. They emerge from complex interactions in our brains. Entropy might provide a middle ground between hard determinism and libertarian free will. The universe follows deterministic laws, but the complexity and information processing involved in consciousness make the outcomes genuinely unpredictable. In practice, we have free will, even if technically everything is determined. Fourth, entropy suggests a naturalistic ethics. We're natural systems. Life fights entropy locally while accepting its increase globally. This is neither good nor evil. It's the nature of existence. Aging and death are not evils to be fought at all costs. They're inevitable consequences of being organized systems in an entropic universe. This doesn't mean we shouldn't care for the sick or elderly. It means accepting mortality as natural. Life creates meaning locally through love, connection, accomplishment, growth, and understanding. Meaning doesn't come from cosmic significance or fighting against nature. It comes from engaging with life despite or because of its temporary nature. Fifth, entropy provides perspective on human significance. We're organized structures in an entropic universe. Our consciousness is a temporary decrease in local entropy. We create order through thought, speech, and action. In the scale of cosmic time, our lives are infinitesimal. Eventually, the sun will die. Earth will become lifeless. The universe will reach heat death. All traces of human civilization will be gone. But we're here now. We're conscious now. We understand entropy and the cosmos now. That understanding itself creates order and meaning. The fact that consciousness can emerge in an entropic universe and contemplate entropy, can understand the principles governing existence, is extraordinary. It's a remarkable achievement of matter organized just right. Understanding entropy doesn't diminish human significance. It contextualizes it. We're significant not because we're central to the cosmos or destined for eternal importance. We're significant because we're conscious observers of the cosmos, able to understand its principles and create beauty and meaning in the face of inevitable entropy. When you drink a hot cup of coffee, the coffee cools down. Molecules in the hot coffee move faster than molecules in the cool air. Through collisions and radiation, energy flows from the hot coffee to the cool air. Eventually, they reach thermal equilibrium, the same temperature. Why does heat always flow from hot to cold, never the reverse? It's entropy. The hot coffee is an ordered state, concentrated energy in one place. The cool air is disordered, energy dispersed. When heat flows from coffee to air, entropy increases. When you try to imagine the reverse, air spontaneously giving energy to the coffee, that would decrease entropy. It would require the air molecules to spontaneously coordinate their motion to transfer energy. Statistically impossible. When you break a glass, it shatters into thousands of pieces. The fragments scatter. Can the glass spontaneously reassemble? No. The intact glass is an ordered state, atoms arranged in a crystalline pattern. Broken glass is disordered, fragments scattered randomly. There are vastly more ways to be broken than intact. Entropy is higher for broken glass. Reassembly would require the fragments to spontaneously arrange precisely, coordinating billions of atoms. Statistically impossible. When you shuffle a deck of cards, it becomes randomized. Can shuffling spontaneously produce a deck ordered by suit and rank? Theoretically possible. You only need to shuffle long enough that eventually, by pure chance, the cards end up in that order. But how long is long enough? For 52 cards, the odds of randomly producing an ordered deck after one shuffle is 1 in 10 to the 68th power. That's 1 followed by 68 zeros. You could shuffle a trillion times per second for the age of the universe and never randomly produce perfect order. So practically, it never happens. This illustrates the statistical nature of the second law. Entropy decrease isn't forbidden. It's just so improbable that we can treat it as impossible. When you inhale a deep breath, you're breathing air molecules that have dispersed throughout the room and the world. Those molecules came from the lungs of everyone who's ever lived. When you exhale, you release carbon dioxide and other gases. They disperse into the air. You've increased entropy by breathing, taking organized molecules in your lungs and exhaling disordered molecules dispersed into the environment. Life itself is a process of increasing entropy while creating local organization through energy metabolism. When you pour milk into coffee and watch it swirl, you're observing fluid dynamics and entropy. The milk is concentrated initially, then it disperses. Stirring increases entropy by creating more surface area between milk and coffee, speeding diffusion. Entropy is why stirring is needed. Without stirring, milk would eventually disperse through diffusion alone, but it would take much longer. Stirring accelerates entropy increase. When you feel tired, you're experiencing the consequence of entropy. Your cells have metabolized glucose and other molecules, producing ATP that powers muscle contractions and neural firing. That metabolic work produces waste heat, dispersing energy. Simultaneously, your neurons fire in complex patterns, creating thought and consciousness. This requires energy. Your brain consumes about 20 watts of power continuously. When you sleep, you allow your cells to repair damage, consolidate memories, reset chemical balances. Sleep is partly about managing entropy, clearing accumulated disorder, preparing for another day of work and entropy generation. Your consciousness itself is an entropic process. Thinking, creating neural patterns, firing synapses, generating thoughts requires energy. Thoughts are low entropy structures in your neural tissue. Creating thoughts increases entropy globally through heat dissipation while creating order locally. In your brain, every conscious moment is an entropic act. Every thought you have generates waste heat. Every time you remember something, you're creating ordered structure at cost of entropy increase elsewhere. Consciousness in an entropic universe is remarkable. It's a process of creating meaning and order through energy metabolism, fully aware that eventually entropy will win. All organized structures, including your consciousness, will eventually dissipate. Yet meaning emerges anyway. Purpose arises. Love exists. Beauty is experienced. Understanding is achieved. Understanding entropy doesn't negate any of this. It contextualizes it. We're conscious despite entropy. We find meaning within it. We create beauty knowing it will decay. Despite our deep understanding of entropy, profound questions remain. First, the low entropy problem. Why did the Big Bang create the universe in such low entropy? This remains one of cosmology's greatest mysteries. Some speculate about cyclic universes or quantum processes that naturally produce low entropy initial conditions. Others suggest anthropic reasoning. We necessarily find ourselves in a low entropy universe because that's the only type where observers can exist. None of these answers is fully satisfying. We truly don't understand the universe's initial conditions. Second, entropy and quantum mechanics. Does entropy emerge from quantum mechanics? If we knew the complete quantum state of a system, could we reverse entropy? Some interpretations of quantum mechanics suggest that information is never truly lost, that apparent irreversibility emerges from coarse graining and imperfect information. If true, entropy would be more subtle than we thought. The black hole information paradox exemplifies this. Does information truly disappear into black holes, or is it encoded in Hawking radiation? Answering this requires reconciling quantum mechanics and general relativity. Third, entropy and consciousness. Does consciousness involve entropy? Do conscious beings necessarily increase entropy at higher rates than unconscious systems? Some researchers speculate about quantum effects in consciousness. Others suggest consciousness is fundamentally about information processing, creating organized patterns. If consciousness involves creating ordered neural patterns, it requires energy. This costs entropy increase. The question is whether consciousness has special thermodynamic properties or whether it's just another phenomenon subject to the second law. Fourth, entropy and the emergence of complexity. How do complex structures emerge if entropy always increases? This isn't actually paradoxical. Complexity emerges in far from equilibrium systems with energy flow, but the details of how complexity arises from simple physics remains mysterious. Life, intelligence, technology, all are complex structures arising from simple particles following simple laws. How this is possible is profound, even if not contradictory to thermodynamics. Fifth, entropy in quantum gravity. If space and time emerge from quantum gravity, does entropy have a fundamental role? Some theories suggest space-time itself emerges from entanglement in quantum systems. If true, entropy and information would be more fundamental than space and time. This is speculative cutting-edge physics. The answers might transform our understanding of reality. Sixth, entropy and the fate of civilization. As civilizations advance, they consume more energy. How long can an advanced civilization sustain itself? Eventually, entropy limits catch up. The star dies. Available energy exhausts. The civilization must either find new energy sources, stop growing, or decline. The Kardashev scale ranks civilizations by energy consumption. A Type 2 civilization would consume a star's entire output. A Type 3 would consume a galaxy's output. Can such civilizations even exist given entropy and thermodynamic limits? These questions remain open, but they all stem from entropy, one of physics' most fundamental principles. What I've been trying to convey throughout this video is that entropy isn't an abstract concept reserved for physics classes. It's fundamental to existence. Understanding entropy means understanding why time flows forward, why broken things don't spontaneously fix themselves, why you age, why the universe will eventually die, why life requires work and energy. Entropy is why nothing lasts forever. Nothing stays organized without effort. Nothing remains unchanged. This could seem depressing. The universe is slowly dying. Heat death awaits in the incomprehensibly distant future. Everything you build will eventually crumble. Every person you love will eventually die. Every civilization, every species, every star will eventually be gone. But I think understanding entropy is actually liberating. It explains why life is precious, because it's temporary and improbable, because maintaining organization requires constant work, because consciousness and complexity and meaning emerge as rebellion against entropy, fully aware that entropy will eventually win. If the universe were static, unchanging, eternal, maximum entropy always, there would be nothing. No change, no growth, no possibility. The universe would be dead. Instead, we have a universe that's dynamically dying, increasing entropy, but not yet at maximum. A universe where energy flows and structures form, where life emerges and consciousness develops, where meaning is possible because it's temporary. Entropy gives time direction. Entropy makes history real. Entropy is why the past is fixed and the future is open. Entropy is why memory is possible and why you can choose. Living in an entropic universe means accepting impermanence. It means finding meaning locally rather than seeking cosmic significance. It means creating beauty and love and connection while acknowledging they won't last forever. It means building, knowing structures will decay. Learning, knowing you'll forget much of it. Creating, knowing your creations will eventually be destroyed. Loving, knowing loved ones will die. This isn't nihilism, it's realism. And from this realism, meaning emerges. Precisely because nothing lasts forever, how you spend your time matters. Precisely because relationships are temporary, they're precious. Entropy is the most fundamental principle of existence. Understanding it changes everything, not by destroying meaning, but by grounding it in reality. When that 15-year-old me was struck by the realization of entropy, watching steam disperse from a coffee cup, seeing it spread out and become disorder, I felt a kind of existential vertigo. But over years, that vertigo became wonder. Understanding entropy, accepting it, living with it, it made me appreciate this universe we find ourselves in. This strange cosmos where consciousness emerged to understand entropy itself. Entropy is why there's something rather than nothing. Entropy is why the universe is dying. Entropy is why you're alive, aware, able to contemplate these ideas. Entropy plays a crucial role in chemistry, determining which reactions proceed spontaneously and which require work. In a chemical reaction, you need to consider both enthalpy, heat, and entropy. The Gibbs free energy combines them. G equals H minus Ts, where H is enthalpy, T is absolute temperature, and S is entropy. A reaction proceeds spontaneously if the total Gibbs free energy decreases. Delta G is less than 0. This can happen if enthalpy decreases, exothermic heat-releasing reaction, or if entropy increases significantly, endothermic but entropy-increasing reaction. Remarkably, some reactions absorb heat, delta H greater than 0, yet proceed spontaneously because they increase entropy, delta S greater than 0, enough that T delta S exceeds delta H. This shows that spontaneity isn't just about releasing energy. It's also about disorder. Reactions that produce more disorder, more molecules from fewer, gases from liquids, dispersed products, are favored entropically. For instance, dissolving salt in water is endothermic. It absorbs heat. Yet salt spontaneously dissolves because the ordered crystal structure breaks apart into dispersed ions and hydrated molecules. Entropy increases, overcoming the enthalpy cost. Protein folding is another entropy phenomenon. A protein chain can fold into countless conformations, a huge number of microstates. The folded conformation is lower entropy. There's only one or a few stable folded structures. So entropy would seem to favor unfolded states. Yet proteins spontaneously fold. Why? Because water entropy increases when proteins fold. Unfolded hydrophobic amino acids are exposed to water, forcing water molecules into ordered cages around them. Folding buries hydrophobic residues inside, allowing water molecules to be released. Water entropy increases significantly. The hydrophobic effect, the tendency of nonpolar molecules to cluster in water, is entirely an entropy effect. It's not that nonpolar molecules attract each other. It's that water's entropy increases when it doesn't have to cage nonpolar molecules. This illustrates how entropy can be counterintuitive. Protein folding decreases protein entropy, but increases water entropy, and the water entropy increase dominates, so folding is favorable. Catalysts, molecules that speed up reactions, work by lowering the activation energy. They don't change whether a reaction is favorable. They don't change the delta G. They just make the reaction proceed faster by providing an alternative pathway with lower energy barriers. Without catalysts, many favorable reactions proceed extremely slowly because they require high energy transition states. Catalysts lower these energy barriers. Enzymes are biological catalysts. They're proteins that fold into shapes that bind reactants, stabilize transition states, and speed up reactions by factors of millions or billions. All of this is rooted in entropy, both thermodynamic entropy, disorder, and information entropy, uncertainty, which guides protein folding and enzyme binding. A phase transition, water boiling, ice melting, metal becoming magnetic, involves dramatic changes in entropy. When ice melts to water, the crystalline structure breaks down. Molecules that were locked in rigid positions now move freely. This increases entropy significantly. This is why melting is a spontaneous process above the melting point. The enthalpy cost of breaking ice's crystal structure, energy needed, is less than the entropy benefit from water's freedom, T delta S term. Below the melting point, the entropy cost of forming ice exceeds the enthalpy benefit, so ice is stable. When water boils to steam, the entropy change is even more dramatic. In liquid water, molecules move freely but are still in contact. In steam, molecules are dispersed far apart with enormous freedom. Entropy increases hugely. This is why boiling is so endothermic, requires huge energy input. You need to overcome the enthalpy cost, but this is compensated by the enormous entropy increase. Critical points are fascinating. At the critical temperature and pressure, the distinction between liquid and gas disappears. Density is intermediate. The system is unstable to small fluctuations. Entropy is maximal in this state. Supercritical fluids. Fluids above their critical point behave strangely, with properties between liquids and gases. They're used in some industrial processes because of their unique dissolving properties. Magnetic phase transitions are also entropy related. In a ferromagnet, below the critical temperature, electron spins align, creating order, low entropy. Above the critical temperature, spins point randomly, creating disorder, high entropy. The transition occurs because above the critical temperature, the entropy gained from random orientation exceeds the enthalpy cost from not aligning. Entropy even explains superconductivity in some cases. At low temperatures, electron pairs can condense into an ordered quantum state, a superconductor. This is lower entropy than normal conduction, but it reduces energy dissipation, heat, lowering total free energy. The interplay between entropy and energy in phase transition shows that understanding chemistry requires considering both. Entropy affects not just physics and chemistry, but human civilization too. Cities are low entropy structures, organized arrangements of buildings, streets, infrastructure. Creating and maintaining cities requires enormous energy input. Once that energy input stops, cities decay. Ruins become disorder. Technology is low entropy. A computer is an organized structure of silicon, metals, and other materials arranged precisely. This requires energy to manufacture. Once made, technology gradually degrades, entropy increasing unless maintained. Information in books, databases, servers is low entropy. It's organized knowledge. Preserving information requires work. Making copies, checking for corruption, storing in stable media. Without maintenance, information degrades and is lost. Human knowledge itself is low entropy. We've organized information from physics to history into conceptual structures. This requires energy from education systems, research institutions, publishing. Knowledge is maintained through social transmission. Climate change is an entropy problem. We take organized chemical energy, fossil fuels, and convert it to disordered heat, waste heat in atmosphere. This increases entropy and disrupts climate systems. Renewable energy is better because it captures energy that's already being dissipated, sunlight, wind, water flow, and converts it to electricity more efficiently with less waste heat. Economic inequality has entropy implications. When wealth concentrates, low entropy, it requires active maintenance through power structures. When wealth disperses, high entropy, it's the natural equilibrium. Maintaining inequality requires constant enforcement. This doesn't mean equality emerges naturally. It means maintaining inequality requires work. The second law suggests that over long timescales without intervention, systems tend toward dispersed equilibrium states. Social order is low entropy. Societies are organized structures requiring energy, from enforcement of laws, education, coordination. Without energy input, societies decay into chaos. Entropy increases. Agriculture is low entropy farming. Organizing crops, maintaining fields, preventing pest populations from exploding, all require work. Without that work, farms revert to wild chaos. Entropy increases. All of human civilization is a low entropy structure maintained by constant work. We're conscious, organized beings in an entropic universe. The second law of thermodynamics wasn't discovered all at once. It emerged gradually from observations about heat, work, and energy. In the early 1800s, scientists noted that heat engines, devices that extract work from heat, could never be perfectly efficient. Nicolas Carnot analyzed the theoretical maximum efficiency for engines operating between two temperatures. Rudolf Clausius formulated the concept of entropy in 1865, defining it through heat and temperature. He recognized that entropy always increases in isolated systems. Ludwig Boltzmann later reinterpreted entropy statistically, defining it as related to the number of possible microscopic arrangements. This was revolutionary. It connected macroscopic thermodynamics to microscopic particles. Boltzmann faced enormous skepticism. Many physicists of his time believed atoms might not even exist. The idea that macroscopic properties like temperature and entropy emerge from average microscopic behavior was radical. Boltzmann became depressed by the resistance to his ideas. He eventually took his own life in 1906, just before experimental evidence for atoms conclusively vindicated him. James Clerk Maxwell contributed to entropy theory through his thought experiment about the demon. He also developed kinetic theory, showing that temperature is related to average molecular motion. After Boltzmann, the statistical interpretation of entropy became standard. It explained why the second law works, not because some cosmic principle forbids entropy decrease, but because disorder is statistically far more likely than order. In the 1900s, Einstein built on statistical mechanics. He used entropy concepts in his work on statistical mechanics and relativity. In the 1970s, Ilya Prigogine developed non-equilibrium thermodynamics, extending entropy concepts to far from equilibrium systems. This explained how structures form and complexity emerges despite entropy increase. Recent developments connect entropy to quantum information theory, black hole thermodynamics, and the holographic principle. The history of entropy reveals how scientific understanding evolves, from empirical observations to mathematical formulations, to physical interpretation to experimental verification. The second law is one of humanity's great intellectual achievements, understanding a fundamental principle governing all of reality. One of the deepest questions about entropy is, how do complex structures emerge in an entropic universe? The answer involves far from equilibrium systems with energy flow. In equilibrium, maximum entropy, nothing happens. No change, no structure, no complexity. But the universe isn't in equilibrium. Energy from the Big Bang is still dispersing. The sun is converting hydrogen to helium, radiating energy. Energy flows through Earth. In this energy flow, gradients develop. Temperature gradients create convection currents. Chemical gradients drive reactions. This energy flow, far from equilibrium, allows complexity to emerge. This is the regime where Ilya Pigogin's non-equilibrium thermodynamics applies. In far from equilibrium systems, self-organizing structures can emerge, patterns that create order locally while increasing total entropy globally. Examples include convection currents, heat a fluid from below, and geometric patterns of rising and falling fluid emerge. Convection cells. Order emerges from chaos driven by energy flow, chemical oscillations. Certain chemical reactions maintain oscillating concentrations, periodic patterns. These dissipative structures emerge through chemical non-equilibrium dynamics. Life itself. Living systems are far from equilibrium structures maintained by metabolizing energy. Complexity emerges through evolution and development. Consciousness. Brains are complex organizations of neurons that maintain themselves through metabolism. Thought is a dissipative structure. Intelligence and technology. All human innovation and creation is far from equilibrium structure maintained through energy consumption. The key insight: entropy increase permits complexity to emerge. Complex structures require energy flow. As long as energy flows through a system, creating gradients, order can be created locally while total entropy increases globally. This is why life is possible in an entropic universe. The sun provides energy gradient. Life harnesses this gradient to create order. Plants, animals, brains, civilizations. Eventually the sun will die. The energy gradient that powered life will disappear. Then entropy will take over completely. Order will decay. Life will end. But for billions of years, the energy flow from the sun enabled the emergence of remarkable complexity: life, intelligence, consciousness. This is the dance between entropy and complexity. Entropy allows complexity to emerge by driving energy flows, but entropy also ensures complexity is temporary. When energy flows stop, entropy reclaims everything. At human scales, probability behaves strangely when dealing with large numbers. Consider a room with 10 to the 24th power air molecules, roughly the number in a liter of air. Imagine a partition dividing the room in half. What's the probability that all molecules end up on one side? For each molecule, there's a 50% chance of being on the left. With 10 to the 24th power molecules, the probability of all being on the left is 0.5 to the power of 10 to the 24th. This is an incomprehensibly small number. It's not just unlikely, it's effectively impossible. In fact, the probability is so small that if you wrote it in decimal form, there wouldn't be enough atoms in the observable universe to write the digits. To make this concrete, Suppose you waited for one molecule to randomly move from one side to the other per 8 to the nanosecond. You could wait 10 to the power of 100 times the age of the universe and never observe this event. This illustrates why the second law is so reliable. At human scales, entropy decrease is so monumentally improbable that it's indistinguishable from impossible. Yet at small scales, entropy fluctuations can be observed. With only thousands of molecules, you might observe temporary clustering. With millions, fluctuations become rarer. With 10 to the 24th power, fluctuations are undetectable. This is why Boltzmann's constant, the conversion factor between molecular scale and human scale thermodynamics, is so tiny. If systems were made of fewer particles, entropy fluctuations would be common. Bridges would randomly collapse. Coffee would spontaneously boil. The universe would be chaotic. Instead, we have a universe where entropy behaves reliably at human scales because human scale systems contain such enormous numbers of particles. This reliability of entropy at large scales is crucial for life and technology. If entropy decreased frequently, you couldn't build structures, store information, or exist as an organized entity. The second law isn't absolute at small scales, but it's effectively absolute where we live, at scales with trillions of particles. Here's something profound. Measuring a system changes its entropy. In quantum mechanics, measurement causes wave function collapse. Before measurement, a quantum system is in superposition, multiple possible states simultaneously. Measurement selects one state. This selection is an entropy change. You go from uncertainty, many possible states, to certainty, one specific state. Entropy appears to decrease, but it doesn't violate the second law because measuring requires interaction. The measurement apparatus must interact with the system, exchanging particles or energy. This interaction increases the total entropy of the system plus apparatus more than the decrease from the system alone. Maxwell's demon fails because the demon must observe molecules to sort them. The observation costs entropy. In thermodynamics, precise measurements require careful isolation. A thermometer disturbs the system it measures. A barometer disrupts air pressure. Perfect measurements are impossible without energy cost. This connects to Heisenberg's uncertainty principle. You can't know both position and momentum precisely. The limitations on knowledge aren't just epistemic about our knowledge, but ontological about reality itself. In information theory, measurement creates information. Before measurement, you have uncertainty. After you have definite knowledge, information. This information has physical cost. The Landauer limit tells us erasing information costs energy. So measurement, information, and entropy are intimately connected. Knowing something about a system requires the system to have lower entropy, be more specific, or requires increasing entropy elsewhere in the measurement apparatus or environment. This is why perfect measurement is impossible, why perfect knowledge is impossible, why observation affects reality. Entropy isn't just a property of systems, it's related to how we know systems. What we can measure, what information we can extract, what knowledge we can gain, all are bounded by entropy. Does entropy imply determinism or indeterminism? At the microscopic level, quantum mechanics is indeterministic. Particles behave probabilistically. Their exact positions and moment can't be known simultaneously. At the macroscopic level, due to enormous numbers of particles, statistical laws take over. Behavior becomes deterministic in a practical sense. Entropy mediates between these scales. In a fully deterministic universe, one where particle positions and velocities could be known perfectly and evolve precisely, time could be reversed. Given perfect information about the present state, you could compute the past perfectly. But entropy introduces a barrier. You can't have perfect information about macroscopic systems because there are too many microstates consistent with any macroscopic state. From an observer's perspective, with finite information, the future is uncertain, but the past is fixed. This creates time's arrow. Entropy increases your uncertainty about microscopic details as time progresses forward. This functional irreversibility from an information perspective, emerges even if fundamental laws are time symmetric. Some philosophers argue this means determinism and free will are compatible. Even if the universe is deterministic at the microscopic level, from any finite observer's perspective, the future appears open and the past fixed. This functional perspective, what matters for agency and choice, is what's physically relevant. If you can't predict your own choices, they're effectively free, even if they're technically determined. Entropy provides a framework for understanding determinism, freedom, and the arrow of time consistently. Entropy is often presented as depressing. The universe is dying. Heat death awaits. Everything decays. Death is inevitable. But I think understanding entropy is actually profound and beautiful. It explains why existence matters. If the universe existed in maximum entropy forever, static, unchanging, perfect chaos, there would be nothing. No structure, no life, no consciousness, no possibility. But the universe started in low entropy. Since then, it's been increasing. This process, entropy increase, is what allows existence as we know it. Stars form, fuse hydrogen, radiate energy, die. In their death, they create heavier elements. These elements are spread into space. New stars and planets form. Life emerges. Consciousness develops. Civilizations arise. All of this is possible because entropy is increasing, because energy is flowing, because the universe hasn't reached maximum entropy yet. The second law, entropy always increases, is what gives the universe direction. It's what makes time flow. It's what makes history real. It's what makes the future open and the past fixed. Entropy explains why you can remember the past but not the future, why you can influence the future but not the past, why choice is possible. Entropy explains why you age and must eventually die, but it also explains why you're alive now, why consciousness is possible, why meaning exists. Mortality is the natural consequence of being ordered structures in an entropic universe. Death isn't a failure or tragedy, it's thermodynamic necessity. But the fact that you exist at all, that consciousness emerges and persists, that you can understand these principles, that's miraculous. When you understand entropy, you understand that you're engaged in a temporary rebellion against the universe's tendency toward disorder. Your life, your mind, your consciousness are low entropy structures maintained through metabolizing energy. When you die, that energy input stops. Entropy takes over. Your ordered structures decay into disorder. But while you're alive, you have something precious, consciousness in an infinite, indifferent, entropic universe, the ability to understand, the capacity for love, the possibility of meaning. That's enough. That's everything. Entropy isn't depressing. It's liberation. It's the reason existence is possible. It's the arrow that points toward meaning. I mentioned the low entropy problem of cosmology, why the Big Bang started in low entropy. Let me explore this more deeply. The puzzle is stark. If entropy always increases, shouldn't systems naturally evolve toward maximum entropy? Yet the Big Bang created the universe in extraordinarily low entropy. This seems backwards. If entropy always increases, shouldn't the initial state be maximum entropy? The resolution involves understanding what low entropy means. Entropy is typically defined relative to a given set of constraints. If you have a gas in a box, low entropy means all molecules are in one corner. High entropy means they're spread throughout. But at the Big Bang, what were the constraints? What was the initial state relative to? One possibility, quantum gravity makes the notion of initial state more subtle. Maybe at the Planck scale, classical notions of initial conditions break down. Maybe the Big Bang involves quantum processes we don't yet understand. Another possibility, the universe isn't unique. Maybe there are infinitely many universes with different initial conditions. We observe low entropy universe because we require a low entropy universe to exist as observers. This is the anthropic reasoning. A third possibility, entropy is fundamentally different at cosmological scales. Maybe what we call low entropy isn't actually low relative to some deeper principle we don't yet understand. A fourth possibility, time itself might be different. Maybe the Big Bang didn't happen at a particular moment, but exists outside time. Or maybe the notion of causality and entropy only apply after some cutoff. A fifth possibility, there's a fundamental principle selecting low entropy initial conditions that we haven't discovered. Maybe initial conditions are special, maximally constrained, minimally entropic. This paradox remains unsolved. It's one of the deepest mysteries in physics. The resolution will probably require insights from quantum gravity, mathematics, or philosophy that we don't yet have. But the puzzle itself is profound. It suggests that entropy and thermodynamics touch on fundamental questions about why the universe exists and why it has the properties it does. Why do so many people find entropy confusing? Why isn't it more intuitive? Part of the issue is that entropy is fundamentally statistical. It's about probability and large numbers. Our intuitions evolved in a world of medium-sized objects, things we can hold and manipulate. We have good intuitions about balls and sticks and everyday objects. We have poor intuitions about probabilities, statistics, and large numbers. When you hear entropy is disorder, you think about messy rooms and scattered objects. But thermodynamic entropy isn't about messiness. It's about the number of microscopic arrangements. A deck of shuffled cards looks disordered but has many possible arrangements. A deck arranged by suit and rank looks ordered but has few arrangements. For thermodynamic entropy, the shuffle state has higher entropy, not because it looks messier, but because there are more ways for cards to be shuffled than organized. Another intuitive problem, we think of entropy as a property of a system, but really it's a property of our knowledge about the system. If you knew the exact position and velocity of every molecule in a gas, the entropy would be zero from your perspective. You'd have perfect information, but the gas would still look chaotic to anyone else. Entropy isn't objective in that sense. It depends on the information available to you. Yet another issue, entropy seems to act like a force or agent, pushing toward disorder. But there's no force. Entropy isn't something doing anything. It's just a consequence of probability. A gas expands to fill a container not because it's trying to maximize entropy, but because there are so many more configurations with molecules spread throughout than confined to one corner. Statistically, spread out configuration is overwhelmingly likely. Our brains evolved to think about agents, animals with intentions. We anthropomorphize entropy as if it's an entity with goals. Entropy wants to increase. But entropy is just mathematics applied to large numbers. These intuitive difficulties explain why even smart people find entropy hard to grasp. The concept requires statistical thinking that our brains didn't evolve to perform. But once you get it, once you understand that entropy is about probability, that the second law is statistical inevitability, not physical force, entropy stops seeming mysterious. It becomes obvious. The universe tends toward high entropy states because there are simply more of them. That's all. Simple. Profound. True. Artificial intelligence faces entropy limits that are often overlooked. Every computation dissipates heat, heat that must be dissipated into the environment. As AI systems become more powerful, more complex, they must dissipate more heat. The Landauer limit sets a minimum energy cost per bit of computation. This isn't a limitation of current technology. It's a fundamental physical limit set by thermodynamics. As AI becomes more advanced with larger models, more parameters, more computations per second, energy consumption increases non-linearly. Current large language models already consume enormous energy. Training them uses electricity equivalent to powering thousands of homes. Future AI systems, if they're to be orders of magnitude more powerful, will face escalating energy costs, not just technologically, but thermodynamically. There's a question about what happens if we try to create super intelligent AI. How much computation would be required for general artificial intelligence? For entities far exceeding human intelligence? Thermodynamics suggests there might be limits. At some point, the energy required to run a system at speeds faster than biological neurons might exceed practical bounds. This doesn't mean superintelligence is impossible. It means it might require enormous energy or operate at slower speeds than we imagine, or it might require new computational paradigms we haven't conceived of. Entropy doesn't forbid superintelligence. It just means superintelligence has a thermodynamic cost. This has implications for technological civilization. As technology becomes more advanced, energy consumption increases. Eventually, a civilization might become limited by available energy, not by computational capability. I should mention that while the second law is extraordinarily reliable, physicists occasionally speculate about alternatives. Some theories propose that entropy might reverse in extreme conditions, near black hole singularities in quantum gravity regime, or in conditions we haven't yet discovered. Others speculate about universes with different entropy arrows, universes where entropy increases in the opposite direction. In such universes, observers would experience time flowing backward from our perspective. Some cosmological theories propose CPT symmetry violations, where charge, parity, and time symmetries might not hold universally. Others explore whether entropy could be a fundamental law or might emerge from deeper principles. These are speculations on the frontier of physics. Current evidence overwhelmingly supports entropy increase as a fundamental principle, but the fact that physicists continue to question it shows that science remains open to revisions. If new evidence suggested entropy could decrease, physics would accommodate it. That's the nature of science. It's built on evidence. When evidence changes, understanding evolves. Right now, evidence supports that entropy always increases. This principle is one of physics's most reliable foundations. But recognition that it could be wrong in principle, that it's testable in principle, that it could be overturned keeps physics honest. This is how scientific knowledge works. Provisional, testable, subject to revision, but based on best evidence available. Entropy is our best understanding of how the universe works, and it works extraordinarily well. Here's a strange implication of entropy that few people contemplate. What does entropy say about personal identity over time? You are not the same collection of atoms you were 7 years ago. Most of your atoms have been replaced. You've consumed food, converted it to energy, expelled waste. Over time, nearly every atom in your body has been exchanged, yet you feel like the same person. Why? Identity isn't about the specific atoms. It's about the pattern. The organization of matter. Your cells maintain themselves by reproducing. Your memories are patterns in your brain. Your personality is a stable pattern of behavior. As long as the pattern is maintained, replacing atoms but keeping the organization intact, you remain yourself. But maintaining this pattern requires work. It requires energy. It requires fighting entropy. Your body constantly repairs damage, replaces old cells, maintains organization. When you sleep, cells repair themselves. When you eat, you get energy to maintain organization. Without this maintenance, without fighting entropy, you'd decay. Your pattern would dissolve into disorder. Death is when the pattern completely breaks down. Without energy input, your cells degrade. Your memories fade, decomposition. Your organization dissipates into environment. The pattern that was you is gone. This raises philosophical questions. If you were gradually replaced atom by atom, at what point would you cease to be you? If a perfect duplicate of your brain were created, would it be you or someone else? These are questions philosophers have debated for millennia. Entropy provides a physical perspective. You're a pattern maintained against entropy through energy consumption. As long as the pattern persists, you persist. When the pattern dissolves, you cease to exist. This isn't mystical or dualistic. It's physics applied to biology. That moment crystallized something profound for me. The vapor, water molecules that had been concentrated in boiling liquid, spreading out into the air, never to reconcentrate, never to spontaneously boil again. Gone. That's entropy. That's time. That's irreversibility. For many people, this is depressing. The universe is dying. Everything falls apart. Death is inevitable. But I've come to see it as liberating. If entropy were reversed, if ordered things, spontaneously organized, if dispersion reversed, if time flowed backward, nothing would happen. The universe would be static. There would be no history, no change, no possibility. Entropy is what makes change possible, what makes time flow, what makes life possible. Life exists because energy flows from the sun into Earth, because that energy creates gradients, because gradients enable complexity. Consciousness exists because brains harness energy to create organized neural patterns, because those patterns think and feel and wonder. Entropy is what drives all of this. Entropy is what creates possibility. Yes, eventually everything will decay. The sun will burn out. The universe will reach maximum entropy. All structure will dissolve. But that's trillions of years away. Right now, in this moment, entropy is driving existence, driving life, driving consciousness. You are here. You are aware. You can understand these principles. You can create meaning and beauty and connection. That's extraordinary. That's miraculous. That's the gift of living in an entropic universe. When you understand entropy, you understand why existence is possible, why time flows, why you can remember the past but not the future, why you can influence the future but not the past, why love is precious because it doesn't last forever. Understanding entropy grounds meaning in reality. It doesn't diminish meaning, it anchors it. So next time you watch steam rise from hot coffee and dissipate into air, remember what you're witnessing. You're watching entropy increase, time flowing forward, the arrow that points toward the future. And you're part of that process. You're an ordered structure in an entropic universe, a temporary rebellion against disorder, a conscious observer of the cosmos. Inal section. Entropy's role in physics, biology, and philosophy. I want to tie together all the threads we've explored and show how entropy connects physics, biology, and philosophy into a unified whole. In physics, entropy is a measure of disorder. More precisely, the number of microscopic configurations consistent with a macroscopic state. The second law states that entropy always increases in isolated systems. This law isn't fundamental in the way, say, energy conservation is. It's a statistical law emerging from probability. But it's more reliable than any other physical principle because it rests on overwhelming probability. In biology, life is a process of fighting entropy locally while allowing it to increase globally. Organisms take ordered chemical energy, food, extract useful work, metabolism, and produce disorder, heat, waste. Complex structures, cells, organs, brains persist through continuous energy expenditure. When energy input stops, death, entropy rapidly increases. The body decays. Organization dissolves into disorder. Aging is entropy. Mutations accumulate. Damage exceeds repair. Entropy increases faster than biological systems can counteract. Evolution works within entropy constraints. Natural selection favors organisms efficient at capturing energy and maintaining low entropy organization. More efficient photosynthesis, better predators, more intelligent brains. All are ways organisms compete to harness energy and maintain order against entropy. In philosophy, entropy provides grounding for several concepts. Time's arrow emerges from entropy. The forward direction of time is the direction of increasing entropy. Time isn't fundamental, it emerges from this statistical tendency. Free will becomes compatible with determinism. Even if the universe is deterministic at the microscopic level, from any observer's perspective with finite information, the future is uncertain while the past is fixed. This functional asymmetry gives practical free will. Meaning emerges naturally from finitude. Because life is temporary, because entropy guarantees death, meaning doesn't require cosmic significance. Meaning arises from engagement with existence in the face of mortality. Mortality loses its horror when understood through entropy. Death isn't tragic. It's inevitable consequence of being ordered structures in an entropic universe. What's remarkable isn't that you'll die, but that you're alive now, conscious, able to understand these principles. The second law is extraordinarily successful. We've never observed it violated. It explains phenomena from everyday life to cosmic evolution. It constrains technology and physics. Yet the second law is statistical. It's not absolute. In principle, entropy could decrease. It's just so monumentally improbable at human scales that we treat it as impossible. This reveals something about scientific laws. They're not abstract truths existing in some Platonic realm. They're descriptions of how the universe behaves, grounded in evidence and mathematics. A law can be true and probabilistic. A law can be essentially reliable while technically not absolute. This understanding prevents misinterpretation of science. When we say the second law is absolute, we mean it's effectively absolute within the domains we observe. We mean it's so well supported by evidence and reasoning that treating it as absolute is justified practically. But we remain open to the possibility of correction if new evidence emerges. This is the difference between science and dogma. Dogma says, this is true and unquestionable. Science says, this is our best understanding based on evidence, and we remain open to revision if evidence warrants. Entropy teaches this lesson well. It's one of the most reliable principles in science. Yet it's also probabilistic, with theoretical limits, and subject to revision if quantum gravity reveals something unexpected. The best scientific thinking holds both: confidence in well-supported principles and openness to revolutionary revision if evidence demands it. Understanding entropy thus teaches us how to think scientifically, how to balance confidence with humility, how to build reliable understanding while remaining ready to be wrong. In economics, entropy concepts apply to market dynamics. Markets tend toward equilibrium, maximum entropy, unless external forces maintain disequilibrium. Monopolies concentrate wealth, low entropy. Free competition disperses it, high entropy. Maintaining wealth concentration requires active enforcement through law and institutions. Entropy tends to disperse it. In psychology, entropy appears in cognitive science. Your brain maintains itself against entropy by constantly processing information, creating memories, organizing thoughts. Mental fatigue is partly entropic, your brain's organization degrading. Sleep allows mental organization to be restored. Dreams might be the brain defragmenting, sorting and organizing information accumulated during waking hours. In linguistics, entropy appears in language evolution. Languages drift toward more common, more variable forms, high entropy, unless written standards and institutions maintain consistency, low entropy. In ecology, entropy determines ecosystem stability. Diverse ecosystems, high entropy, are more stable than monocultures, low entropy, because diverse systems can tolerate perturbations better. In art and music, entropy appears subtly. Perfect order, zero entropy. A constant note, a uniform color, is boring. Maximum entropy, pure noise, random patterns, is also uninteresting. Beauty often lies between. Enough order to perceive structure, enough randomness to be interesting. This is sometimes called the complexity sweet spot or the edge of chaos. In social systems, entropy dynamics determine stability. Highly unequal societies, low entropy, require constant enforcement to maintain. Entropic tendency is toward equality, high entropy. This doesn't mean equality emerges naturally, it means maintaining inequality requires work. The thermodynamic cost of social inequality is enforcement energy. All of these applications flow from the same principle. Entropy tends to increase unless work maintains organization. Entropy isn't just abstract physics. It shapes your daily experience in ways you probably don't consciously recognize. Your experience of time flowing forward is entropy. Your neurons fire in patterns determined by past inputs. Those neural patterns create memory of the past and anticipation of the future. The arrow from past to future is defined by entropy, the direction of increase. Your sense of causality, that causes precede effects, flows from entropy. Causes can increase entropy. Disorder is likely. So causes tend to occur before effects. Reversing this would require entropy to decrease, which is practically impossible. Your emotional attachment to the present moment, your sense that now is special, real, compared to the past and future, emerges from thermodynamics. The present is where your information is certain. The past is fixed by now fixed. Low entropy conditions. The future is uncertain because it's high entropy. Many possibilities. Your drive to consume, to eat, to accumulate, to use energy is fundamentally about fighting entropy. Your body needs energy to maintain organization. Without it, you decay. Hunger is your body signaling that energy stores are depleting. Your need for sleep is entropy related. During waking, your brain metabolizes energy, creating neural patterns, maintaining consciousness. This is thermodynamically expensive. Sleep allows repair and restoration. Your attraction to love and connection is, at its core, about shared low entropy structures. Two people coordinating behavior, sharing information, creating mutual order through interaction. Your creativity, your ability to generate novel ideas, emerges from your brain's complexity. Complex systems can generate seemingly infinite variations because they have so many internal states. Creativity is your brain exploring its own thermodynamic complexity. Your mortality, your aging, and eventual death is entropy winning. Your body can only fight entropy for so long. Eventually, damage accumulates faster than repair. Organization degrades, death results. Understanding that these experiences are rooted in thermodynamics doesn't diminish them, it grounds them. It explains why they're inevitable and precious. Absolutely final section: where we are and where we're going. Throughout this exploration, we've traveled from the basics of entropy, how disorder is statistically more likely than order, to its implications for consciousness, time, meaning, and mortality. We've seen that entropy explains why time flows in one direction only, sets limits on technology and computation, determines what's possible in chemistry and physics, shapes biology and evolution, constrains artificial intelligence and civilization, anchors meaning in our finite lives. Where do we stand in understanding entropy? At one level, we understand it deeply. We have precise mathematical formulations. We can predict thermodynamic behavior with extraordinary accuracy. We've built technologies based on thermodynamic principles. But at another level, profound mysteries remain. Why did the universe start in low entropy? What's the relationship between thermodynamic entropy and information entropy? How does entropy relate to quantum gravity? Can entropy decrease under extreme conditions? What role does entropy play in consciousness? These questions mark the frontier of our understanding. They're the problems that will drive physics research for decades to come. As our understanding evolves, one thing seems certain: entropy will remain central. It's too fundamental, too reliable, too deeply connected to existence itself to be superseded. Future physics will probably reframe entropy, connect it more deeply to information and quantum mechanics, extend it into domains we haven't yet explored. But entropy itself won't disappear from our understanding. Why? Because entropy, at its core, is about probability. And probability underlies all of physics once you dig deep enough. So entropy will be with us. It will continue to shape how we understand the universe, how we build technology, how we think about existence. And that's beautiful, because entropy is what makes existence possible. Entropy is what gives time direction. Entropy is what makes life remarkable. Entropy is what makes consciousness worth understanding. If you take nothing else from this video, remember this: you're a temporary rebellion against entropy. You're an organized structure in an entropy-increasing universe. Your consciousness is a pattern maintained through energy expenditure. Your life is a brief window during which low entropy energy flow allows complexity to exist. This isn't depressing. It's liberating. It grounds meaning not in cosmic significance, but in the simple fact that you're here, aware, able to understand. Entropy is why that matters. Entropy is the beautiful tragedy of existence. It's beautiful because it makes life possible. It's tragic because it guarantees endings. The universe started in extraordinary order, low entropy. It has been becoming more disordered ever since. This process of increasing entropy defined time's arrow, created the conditions for life, enabled consciousness. If the universe had always existed in maximum entropy, it would be static, unchanging, utterly dead. Nothing would happen. There would be no time, no change, no possibility. But we don't live in maximum entropy. We live in an era when energy still flows, when gradients exist, when complexity can emerge and persist. This era is temporary. Eventually, the universe will reach maximum entropy. All stars will burn out. All black holes will evaporate. All structure will disperse. Nothing will change. Nothing will happen. Only eternal, unchanging void. This is heat death, the fate of the universe written in thermodynamics. We don't know if this is the end of the story. Maybe the universe cycles. Maybe it branches into new phases. Maybe there are universes beyond ours we can't perceive. But in the thermodynamic universe, we know heat death is inevitable. Yet that doesn't diminish the present. It gives it weight. It gives your life meaning precisely because it's temporary. In this moment, in this era when energy flows and complexity persists, you exist. You're conscious. You're reading these words, thinking these thoughts, experiencing existence. This is extraordinary. This is the cosmic moment you're embedded in, after the Big Bang, but before heat death, after life emerged, but before the sun dies, after intelligence developed, but before the universe becomes entirely cold and dark. You're living in a window of possibility, a brief time when disorder hasn't yet won, when order can persist, when consciousness can contemplate itself. That's remarkable. Entropy is what created that window. Entropy's increase is what allows it to remain open for billions more years. So entropy is both beautiful and tragic. It's the principle that makes existence possible. And it's the principle that guarantees endings. Living consciously with entropy means accepting both truths, appreciating the window we're in while acknowledging it will close, creating meaning while accepting mortality, building, knowing structures will eventually decay, loving, knowing loved ones will die. This isn't nihilism. It's realism grounded in physics. And from that realism, meaning emerges. That's what entropy teaches. That's what I've tried to convey throughout this video. Entropy is the most fundamental principle of existence. Understanding it changes everything about how you see the universe and your place in it. Throughout my life, my relationship with entropy has evolved from fear to acceptance to appreciation. As that 15-year-old watching steam disperse, I felt existential vertigo. The realization that heat flows only one direction, that organization breaks down, that the universe is dying. It was overwhelming. As a young adult studying physics and thermodynamics, I developed intellectual understanding. Entropy was mathematics. It was the second law. It was something I could calculate and understand precisely, but something was missing. I understood entropy intellectually, but hadn't integrated it emotionally. That changed when I experienced loss, losing people I loved, watching biological systems decay, realizing my own mortality. Entropy stopped being abstract. It became lived reality. Heat death became a personal truth, not just cosmological fact. Mortality became immediate, not distant. And something shifted. Understanding entropy's role in mortality didn't make death more frightening. It made it more acceptable, more natural, more okay. Entropy explained why aging happens, why cells degrade, why maintaining organization is exhausting, why eventually maintenance fails. This isn't cosmic tragedy, it's thermodynamic inevitability. And accepting that inevitability freed me to appreciate the present, to value the time I have, to love more deeply knowing it's temporary, to create knowing creation will decay, to learn knowing I'll forget much of it. Understanding entropy became wisdom rather than despair. Now, looking back on those decades, I see a trajectory from fear of entropy to knowledge of entropy to acceptance of entropy. I think that's the journey anyone travels when they truly grapple with entropy. It starts uncomfortable. It becomes intellectual. Finally, if you're lucky, it becomes wisdom. Wisdom isn't just knowledge, it's knowledge integrated with acceptance and perspective. Knowing about entropy is knowing the second law, understanding microstates, calculating thermodynamic values. Understanding entropy is appreciating its role in time, life, consciousness, meaning. Wisdom about entropy is living in full acknowledgement of thermodynamic realities while finding meaning and purpose anyway. That's the synthesis I hope this video provides. Not just the physics of entropy, though we've covered that thoroughly, but the human integration of what entropy means for how to live. Entropy is the most fundamental principle of existence. As I write this in 2026, understanding entropy has never been more important. We face climate change, a crisis fundamentally rooted in thermodynamics. We're taking concentrated chemical energy, fossil fuels, and converting it to dispersed heat, global warming. We're accelerating entropy increase. We face challenges in energy production, technology, computation, all limited by thermodynamic principles. We face questions about artificial intelligence, consciousness, the future of civilization, questions that entropy sheds light on. We face existential questions about meaning in a universe governed by entropy. How to find purpose, knowing everything eventually decays. Understanding entropy isn't just intellectually satisfying, it's practically essential for navigating the challenges ahead. Climatically, we need to understand that energy transitions are constrained by efficiency limits set by entropy. Solar, wind, nuclear all have Carnot limits on efficiency. We can't escape thermodynamic constraints. Technologically, we need to recognize that computation has energy costs that will increase as AI becomes more powerful. Psychologically, we need to ground meaning in reality, accepting mortality while creating purpose anyway. Philosophically, we need to integrate entropy's implications into how we think about time, freedom, and existence. None of these challenges are solvable by ignoring entropy. All require understanding and accepting thermodynamic realities. The 21st century will be shaped by whether we can integrate entropy awareness into our technology, policy, and philosophy. Do we engineer solutions that work with entropy rather than fighting it? Do we find sources of energy that align with increasing entropy? Do we build systems that acknowledge that entropy always increases? Do we create meaning systems that accept mortality and impermanence? These questions will define our civilization's future. Understanding entropy, truly understanding it, is prerequisite for navigating them. That's why I've spent all this time exploring entropy with you, not just because it's fascinating physics, but because it matters. It matters for the future we're building, and it matters for how you understand yourself and your place in the cosmos. Understanding entropy is understanding the deepest principle governing existence. And that understanding, integrated wisely, can guide us toward a future worth inhabiting. Thanks for watching. And thanks for thinking deeply about these ideas. Imagine yourself 50 years from now. You've lived a full life. You've created things. You've loved. You've learned. You've contributed to the world. Your body is older. Your cells have accumulated damage. Your energy levels aren't what they were. Entropy has been winning gradually. But your mind, your consciousness, has accumulated decades of experience, memory, understanding. When you think about your life from that vantage point, what will matter? I believe it will be the connections made, the love given, the understanding developed, the impact on others. None of that lasts forever. Eventually, you'll die. Your body will decay. Your consciousness will cease. The effects of your life will gradually fade into history. But that doesn't make any of it meaningless. Entropy guarantees that everything temporary will end, including you, including everyone you love, including human civilization eventually. But entropy also guarantees that until those endings come, change is possible, growth is possible, connection is possible, meaning is possible. Your life has meaning not despite its temporality, but because of it. The fact that you exist now, in this moment, in this era, when complexity persists and consciousness has emerged, that's what matters. Understanding entropy is understanding why that matters. It's understanding why time flows, why change happens, why you can create and influence and love. It's understanding that the universe isn't hostile to meaning. It's the very nature of entropy that creates space for meaning. So as you look toward your future, whatever comes next for you, do so with this understanding. You're an organized structure in an entropic universe. Your consciousness is temporary. Your life is brief. And that's okay. That's beautiful. That's everything, because in that brief time, in that temporary organization, you can love, create, understand, connect. You can find meaning. You can make a difference. You can leave a mark, however small, not forever. But that was never the requirement for meaning. Entropy is the requirement, and entropy is what makes existence possible. So embrace it, understand it, live with awareness of it. And in that understanding, find not despair, but purpose. That's what entropy teaches. That's what understanding entropy makes possible. That's why it matters. Thanks for watching this extended exploration of entropy. I hope it's given you new ways of thinking about time, meaning, existence, and your place in the cosmos. The universe is governed by entropy. And understanding that governance is understanding everything. One of the deepest mysteries in biology is how life originated from non-living chemistry. Entropy provides constraints on what's possible. Life is extraordinarily organized. DNA has information encoded. Proteins fold into specific shapes. Cells maintain boundaries and internal organization. This organization is profoundly low entropy. The question is, how did such organized structures arise from random chemical processes? The answer isn't that entropy decreased. It's that life learned to harness energy to create local organization while dispersing energy and entropy into the environment. The first self-replicating molecules probably weren't very complex. Simple RNA, strands that could catalyze their own copying. Imperfect copying created variation. Molecules that copied faster spread. Natural selection began. As replication became more efficient, more complex structures emerged. RNA developed proteins. Lipids formed membranes. Cells arose. Metabolism developed. All of this, all of the complexity of life, emerged through a process of harnessing chemical energy gradients to create organization. Life didn't violate entropy. It exploited entropy. The sun provides energy. Photosynthetic organisms capture that energy. Heterotrophic organisms eat photosynthetic organisms. In each step, energy is dispersed as heat. Entropy increases globally. But locally in the living organisms, organization increases. Order emerges. This is the trick life learned. Use external energy flow to create local complexity while allowing entropy to increase globally. This trick works as long as energy flows. When energy flow stops, when the sun dies, life can no longer maintain organization. Entropy will take over. The origin of life was the beginning of the universe's most remarkable low entropy structures. It was entropy's most successful rebellion against itself. Understanding life requires understanding entropy. Understanding how life is possible requires appreciating how entropy enables it. Entropy doesn't just govern physics and biology, it governs social systems too, though this is rarely discussed. A society is an organized structure. Laws, institutions, infrastructure, culture, all are patterns that maintain social organization. Creating and maintaining these structures requires energy and work. Enforcement of laws requires energy. Education systems require resources. Maintaining infrastructure requires constant work. Culture requires transmission through generations. Without this continuous work, social structures decay. Communities drift toward equilibrium, maximum entropy, which is chaos. This is thermodynamically inevitable. Societies are low entropy structures. Without continuous input of effort, attention, resources, they naturally degrade toward disorder. The question societies face is, how much work is worth maintaining order? Some societies collapse because they stop investing in maintenance. Infrastructure degrades. Knowledge is lost. Culture fragments. Entropy increases. Other societies maintain themselves by continuous investment in institutions and education. But there's a limit. Eventually, all societies will collapse. Civilizations rise and fall. Empires fall into ruins. The universe doesn't care about human institutions. Entropy will eventually dissolve them all. This isn't pessimism, it's thermodynamic realism. It suggests that building sustainable societies requires constant work. It suggests that collapse is always possible if work lapses. It suggests that we should value institutions and systems that maintain organization, while accepting that all such systems are temporary. It suggests that meaning in social structures comes not from permanence, but from the fact that they matter in the present, during the time they endure. Understanding entropy should change what you value. If everything eventually decays, if all structures eventually fail, all life eventually ends, all civilizations eventually collapse, what's worth valuing? I think entropy answers this question beautifully. What's worth valuing is what matters in the present, not what lasts forever. Nothing lasts forever. But what creates meaning and connection and beauty now? Relationships are worth valuing. They're temporary. The people you love will die. You will die. But in this moment, connection is real and valuable. Knowledge is worth valuing. It will be forgotten. Even the greatest human achievements will eventually be erased. But acquiring understanding, that's a real achievement happening now. Creation is worth valuing. Every work of art will eventually decay. Every building will crumble. Every book will be forgotten. But the act of creating, that matters. That's valuable in the doing. Love is worth valuing. It's temporary. It ends. But it's the most meaningful experience consciousness can have. These things aren't valuable because they last forever. They're valuable because they're meaningful now. Entropy teaches that permanence isn't possible. So value the present. Value the temporary. Value the process more than the outcome. This isn't stoicism, accepting fate passively. It's active engagement with existence, knowing it's temporary. It's like how sunset is beautiful precisely because it's temporary. If the sun set slowly over hours, it wouldn't be beautiful. It's the transience that creates beauty. Human life is the same. Its beauty comes partly from its transience. We love more deeply knowing we'll lose. We create more urgently knowing our time is finite. Entropy teaches us what to value, and what entropy teaches is value what matters now. Value connection and beauty and understanding. Value the temporary. That's wisdom about entropy. That's how to live in an entropic universe. Entropy wasn't always understood. It emerged gradually through scientific progress. Before entropy, heat and cold were thought to be fluids, caloric and frigoric, that moved between objects. This model was intuitive but wrong. It couldn't explain why friction creates heat, why rubbing objects creates warmth without any new caloric fluid being added. Benjamin Thompson, Count Rumford, observed that cannon boring created unlimited heat through friction. This showed heat wasn't a conserved fluid, it was something else. Eventually, scientists understood heat as motion, the kinetic energy of particles moving rapidly. Temperature is the average kinetic energy of molecular motion. Heat is the flow of that energy. But this understanding still didn't explain why heat flows only from hot to cold. Why doesn't cold ever spontaneously flow from cold to hot? The answer requires entropy. The number of ways a system can be arranged is vastly larger when energy is dispersed than when it's concentrated. Statistically, dispersion is inevitable. This was the revolution entropy brought. It showed that irreversibility, the fact that some processes can't reverse, isn't due to a fundamental asymmetry in forces. It's due to probability. This understanding required thinking statistically about large numbers. It required accepting that microscopic randomness could create macroscopic order. Many physicists initially resisted this. They wanted fundamental laws that explained everything deterministically, not statistical laws that explain why disorder is likely. But the evidence became overwhelming. Entropy was real. Statistical laws were powerful. This acceptance of statistical thinking was revolutionary. It changed how physicists think about causation, mechanism, and explanation. Understanding entropy meant accepting that some phenomena are explained statistically through probability and large numbers, rather than through deterministic mechanism. This changed science. It made quantum mechanics possible. It enabled information theory. It revolutionized how we think about explanation. After all this exploration, physics and biology, philosophy and psychology, past and future, what does it mean to truly understand entropy? It means recognizing that entropy isn't just a technical concept, it's a lens through which to view existence. When you understand entropy, you see it everywhere, in your aging body, in cooling coffee, in decay, in death. But you also see it enabling existence, creating time, allowing change, making consciousness possible. Understanding entropy means accepting that everything is temporary. Nothing lasts forever. All structures eventually decay. All order eventually becomes disorder. All organized systems eventually reach equilibrium. This could be paralyzing. If everything ends, why build? Why create? Why love? But entropy also teaches the opposite. Because everything is temporary, everything that persists is precious. Because time moves in one direction, your choices matter. Because change is inevitable, growth is possible. Because endings are guaranteed, meaning is found in the present. This is the wisdom of entropy. Accept that everything is temporary, and that acceptance liberates you. You don't need permanence to have meaning. You need presence. You need engagement with life as it is now, not as you wish it would be forever. Entropy teaches that the present moment is all you ever have. The past is gone. The future hasn't happened. All you have is now. And now, this moment, right now, as you read these words, is where your life is happening. Entropy teaches that you should be here, fully present, aware of the temporality of existence and the preciousness of this moment. This understanding doesn't come from faith or philosophy. It comes from physics, from understanding how the universe actually works. That's profound. That's the gift entropy gives. Understanding entropy, you understand why mortality isn't tragic. It's the price of existence. Why meaning doesn't require permanence, it requires presence. Why your life matters. Because you're conscious now, in this era when complexity persists. That's entropy's ultimate teaching. That's why it matters. Thanks for watching this extended exploration of entropy. I hope it's given you both understanding and perspective. Understanding entropy is understanding everything. That steam, those water molecules, once concentrated, now dispersed, gone forever into the atmosphere, never to spontaneously reconcentrate, never to reboil. That's entropy. That's time's arrow. That's irreversibility. But here's what's beautiful, that steam carries energy. That dispersed heat will eventually be radiated into space. That energy will travel the cosmos. Nothing is truly lost. It's just transformed. Organized energy becomes disorganized. Concentrated becomes dispersed. But it persists, traveling through the universe in different forms. Your body will decay. But the atoms that compose you will persist. They'll become part of plants, animals, rocks, stars. You'll be distributed throughout the cosmos. Your thoughts will fade, but they'll have shaped others' thoughts. Your ideas will ripple forward in time, influencing future generations. Your life will end. But the pattern of connections you've created will persist. The love you've given, the knowledge you've shared, the beauty you've created, none of it lasts forever. But all of it matters. That's what entropy teaches when you truly understand it. It teaches that everything is temporary, and that's okay. That's beautiful. Because in this moment, in this temporary organization of matter and energy, you exist. You're conscious. You understand. Understanding entropy is understanding the universe. And understanding the universe is the highest achievement consciousness can accomplish. You've done that today. You've thought about the deepest principles governing existence. That's remarkable. That's meaningful. That's worth doing. Entropy is the ultimate principle. Understanding it changes everything, and now you understand. So here we are. At the end of this journey through entropy, we've explored the physics, the mathematics, and the mechanisms. We've explored the implications for time, for life, for consciousness. We've explored the philosophy, the meaning of temporality and mortality. And we've arrived at an understanding that's simultaneously humbling and empowering. Humbling because entropy shows our significance is tiny. We're organized matter in an infinite universe governed by principles we didn't choose. Empowering because entropy shows that our existence is miraculous. The fact that consciousness emerges from this universe is extraordinary. The fact that we can understand these principles is remarkable. Entropy is the foundation of everything. Understanding it, it's understanding existence. And now you do understand. You've spent this time contemplating the deepest principles of physics and philosophy. That contemplation matters. That understanding matters. Because understanding entropy, truly understanding it, changes how you live. It grounds meaning. It accepts mortality. It finds beauty in transience. That's the gift entropy gives. That's why it's worth understanding. Thanks for watching.